Welcome to our bioprocess engineering online tutorial on how to perform a microbial fermentation kinetic analysis on Spreadsheet. Through the bioprocess engineering online tutorials, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, visit us at bioprocessdigital.com. You also learn how to use Spreadsheet software for key bioprocess engineering tasks, including analyzing experimental results, modeling and simulating bioreactors, designing and optimizing bioprocesses, evaluating economic and environmental performance. In the present tutorial, you use a spreadsheet to analyze the experimental kinetics of a bacteria production fermentation. You will learn which microbial and fermentation rates to determine, how to numerically calculate rates on Spreadsheet, and how to characterize the microbial fermentation kinetics. For this kinetic analysis, a Corynebacteria strain is grown in a laboratory fermenter containing 2 liters of medium at a controlled temperature of 35 degrees Celsius. The medium contains an initial 40 grams per liter sugar concentration, namely glucose. The fermentation is started by an initial bacteria inoculation at the concentration of 0.5 grams per liter. The fermenter is continuously aerated and stirred to avoid oxygen limitations. During fermentation, medium samples are taken at various intervals. These samples are analyzed for the concentrations of sugar and dry weight bacteria measured in grams per liter. Starting with an initial sugar concentration of 40 grams per liter, bacterial growth occurs over a 9-hour period. The fermentation process begins with a lag phase lasting 5 hours, during which glucose utilization and bacterial growth are very slow. Subsequently, there is a phase of more rapid sugar consumption and exponential bacterial growth, ultimately reaching a final cell concentration of 18 grams per liter. The kinetic analysis of the batch fermentation addresses the following questions. Which rates of cell growth and sugar consumption to determine? How do these rates vary during the batch fermentation? What is the relationship between the growth rate and sugar consumption rate? When analyzing the kinetics of a microbial fermentation, 2 types of rates are determined. First, the microbial specific rates. These rates characterize the metabolic activity of cells during the fermentation. For growing bacteria cells, the key specific rates are the specific rate of bacteria growth μ, measured in gram cells produced per gram cell an hour, and the specific rate of sugar consumption, Qs, measured in grams sugar consumed per gram cell an hour. The second type of rates are the volumetric fermentation rates. These rates express the intensity of the fermentation process within the fermenter. For bacteria growth, the key volumetric rates are the volumetric rate of cell growth, Rx third, measured in grams cells per liter an hour. This rate is the product of the specific growth rate μ and the concentration of cells X, and the volumetric rate of sugar consumption, Rs third, measured in grams sugar per liter an hour. This rate is the product of the specific sugar consumption rate, Qs, and the concentration of cells X. How are the rates calculated from the experimental results of the batch fermentation? Microbial rates of growth and substrate consumption are determined from the experimentally measured time variations of cell and sugar concentrations. These rates are calculated using instantaneous mass balance relations for the cellular biomass and sugar. For a fermentation component, the instantaneous mass balance on the fermenter that expresses the fundamental principle of mass conservation at each instant is written as inlet rate plus or minus production rate equals outlet rate plus internal variation rate. The second production rate term is positive for the produced biomass, negative for the consumed sugar. For a batch fermentation, there are no inlet rate and outlet rate terms, and the instantaneous balance simplifies to plus or minus production rate equals variation rate. For growing bacterial cells, the instantaneous balance in grams cells per hour for the entire fermentation medium of volume Vr is written as Rx third V equals d Vx over d T. Thus, the volumetric growth rate, Rex third, is calculated as Rx third equals dx over dt. According to this relation, it is the volumetric growth rate, Rx third, that determines the time variation of the cellular concentration. At any time, the volumetric biomass production rate is equal to the time derivative of the biomass concentration, which corresponds to the slope of the tangent to the biomass variation curve. The specific growth rate is then calculated by dividing the volumetric rate, Rx third, by the cell biomass concentration X. For the consumed sugar, the instantaneous sugar balance in grams sugar per hour is minus Rs third V equals dVs over dt. Thus, the volumetric sugar consumption rate, Rs third, is given by Rs third equals minus ds over dt. It is the volumetric sugar consumption rate that determines the time variation of the sugar concentration. At any time, the volumetric sugar consumption rate is equal to the negative of the time derivative of the sugar concentration, thus to the slope of the tangent to the sugar variation curve. The specific sugar consumption rate, QAS, is then calculated by dividing the volumetric rate by the biomass concentration. The time derivatives of the cell and sugar concentrations can be numerically calculated by fitting curves through the experimental biomass and sugar concentrations. The experimental biomass concentration time variation curve shows an initial slow increase, followed by a more rapid increase. This variation in cell concentration over time is best represented by a third-order polynomial curve described by the equation x equals at cubed plus bt squared plus ct plus d. From this curve equation, the derivative at any time is calculated as dx over dt equals 3at squared plus 2 bt plus c. The volumetric biomass production rate is then determined as Rx third equals dx over dt. The experimental sugar concentration time variation curve displays an initial slow decrease followed by a more rapid decrease. This sugar concentration variation with time is also best fitted by a third-order polynomial curve according to the equation S equals at cubed plus bt squared plus ct plus d. From this curve equation, the derivative is calculated at any time as ds over dt equals 3at squared plus 2bt plus c. The volumetric sugar consumption rate is calculated as Rs third equals minus ds over dt. The bacteria fermentation kinetic analysis is carried out on a spreadsheet that contains the following sections: the experimental results table with the measured cells and sugar concentrations during the batch fermentation, the cellular growth rates calculation section, and the sugar consumption rates calculation section. In the cellular growth rate section, you first determine the third-order polynomial curve that best fits the experimental cell concentration variation. The procedure is the following. Transfer from the above experimental results table the cell concentrations X during the batch fermentation. On the graph, add the trend line, third-order polynomial curve, through the experimental points, and display the curve equation. Report the values of the polynomial parameters A, B, and C. With these parameter values, calculate the time derivative of the cell concentration as dx over dt equals 3at squared plus 2bt plus c. Establish the formula at 2 hours and copy-paste it to the following times. Set the volumetric growth rate Rx third equal to dx over dt, and graphically display the time variation of Rx third. Finally, calculate the specific growth rate mu as Rx third divided by x, and graphically display its time variation. In the sugar consumption rate section, you proceed in a similar way to first determine the third-order polynomial curve that best fits the experimental sugar concentration variation. Transfer from the above experimental results table the biomass X and sugar S concentrations during the batch fermentation. On the graph, add the trend line, third-order polynomial curve, through the experimental sugar concentration points, and display the curve equation. Report the values of the polynomial parameters A, B, and C. With these parameter values, calculate the time derivative of the sugar concentration as ds over dt equals 3at squared plus 2bt plus c. Establish the formula at 2 hours and copy-paste it to the following times. Set the volumetric sugar consumption rate Rs third equal to minus ds over dt, and graphically display the time variation of Rs third. Finally, calculate the specific consumption rate Qs equals Rs third divided by x, and graphically display the time variation of Qs. Based on the observed time variations in growth and sugar consumption rates during the batch fermentation, which conclusions can we draw about the kinetic characteristics of bacterial fermentation? The first observation is that the bacteria exhibit similar time variations in specific rates of growth and sugar consumption. Both rates initially increase during the 5-hour lag phase. They then remain relatively constant throughout the subsequent rapid growth phase, with a slight decrease observed towards the end of the batch. Simultaneously, the volumetric rates of growth and sugar consumption increase during fermentation. Both rates exhibit an exponential type increase in fermenter activity driven by the rapid rise in cell concentration following the lag phase. This indicates an exponential increase in fermentation intensity throughout the batch process. When plotting the volumetric sugar consumption rate against the volumetric growth rate, a simple proportional relationship is observed between the two rates. The slope of the resulting straight line indicates a stoichiometric coefficient Ys over x of approximately 2 grams of sugar consumed per gram of cells produced. In this tutorial, you learned how to use a spreadsheet to analyze the kinetics of a bacteria production fermentation. When studying the kinetics of microbial fermentations, 2 types of rates are determined: the microbial specific rates, which describe the metabolic activity of cells, and the volumetric fermentation rates, which represent the intensity of the fermentation process. These rates are conveniently determined in a spreadsheet using numerical derivatives of concentrations. The investigated bacterial growth fermentation is characterized by similar time variations in both the specific and volumetric rates of growth and sugar consumption. If interested, you can gain a deeper insight in microbial fermentations by enrolling to one of our 2 online courses: Microbial Fermentation Processes, Optimize Fermenters Operations, and Simulation, Scale-Up, and Optimal Operation of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering. And be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.